Our solar system appears to be a perfect, predictable machine. The truth is far stranger. Planetary orbits are not neat circles, but paths filled with strange wobbles and unexplained deviations. These are not errors in calculation, but cosmic clues. By the end of this journey, you will understand how these tiny anomalies have reshaped physics, hinted at hidden worlds, and revealed our solar system's chaotic history. Why does Mercury's entire orbit slowly rotate around the Sun? What mysterious force tugged at distant spacecraft as they fled into the void? We are about to explore 25 of the most baffling orbital puzzles ever discovered. Each one tells a story of gravitational intrigue and hidden forces. What do you believe is waiting to be found in the dark just beyond the planets we know? The first and perhaps most famous of these orbital mysteries begins with the innermost planet. For centuries, astronomers tracked Mercury with increasing precision, mapping its tight, elliptical path around the Sun. They noticed something peculiar. The point in its orbit where Mercury comes closest to the Sun, called its perihelion, was not staying fixed. Instead, the entire ellipse was slowly rotating like a hula hoop twisting around a central pole. This slow drift is called a precession, according to Isaac Newton's laws of gravity, accounting for the tugs from all the other known planets. Most of this rotation made sense. But not all of it. A tiny sliver of the motion, an extra 43 arcseconds of shift every century, remained utterly unaccounted for. An arcsecond is an almost impossibly small unit of measurement, 1/3600th of a degree. This discrepancy was minuscule, but it was real, and it haunted physics for decades. It was a persistent whisper that something in our understanding of gravity was incomplete. The solution arrived not from a new planet, but from a revolutionary new idea about the universe itself. Albert Einstein's theory of general relativity proposed that gravity is not a mysterious force acting across space, but rather the result of mass and energy curving the very fabric of spacetime. Objects like the Sun create a deep well in this cosmic fabric, and planets follow the curved paths within that well. For Mercury, orbiting so deep in the Sun's gravitational well, this curvature has a measurable effect. The mathematics of general relativity perfectly predicted that extra 43 arcseconds of precession. When Einstein saw his calculations match the observed anomaly, he reportedly felt his heart palpitate. This was not a minor adjustment, it was a fundamental revelation. The wobble in Mercury's orbit became the first critical proof that our universe operates under Einstein's rules, not Newton's, in the realm of extreme gravity. It was a triumph of thought over observation, where a flaw in a planet's path illuminated the true nature of reality. Mercury's solved mystery gave us a new theory of gravity, but the next anomaly would come from the silent darkness far beyond the planets. In the late 1980s, as scientists tracked the twin Pioneer spacecraft Pioneer 10 and Pioneer 11 on their epic journeys out of the solar system, they noticed something deeply unsettling. Both probes, billions of miles from Earth and coasting on momentum alone, were slowing down slightly more than anyone had predicted. It was a tiny, constant deceleration, a gentle tug back toward the Sun, so faint it was like a feather resting on the spacecraft. But it was there, and it defied every conventional calculation. This was the Pioneer anomaly. For over a decade, it was a ghost in the machine of deep space navigation. Teams of researchers launched exhaustive investigations, meticulously ruling out every obvious culprit. Was it the faint push of solar radiation pressure? No, the effect was too strong and the spacecraft were too far out. Could it be a minuscule fuel leak from their thrusters, giving them an unseen kick? Every possible mechanical explanation was checked and rechecked, and nothing fit. The anomaly persisted, a whisper of an unknown force acting on humanity's farthest-flung emissaries. This led to thrilling and sometimes wild speculation. Could it be evidence of dark matter subtly dragging on the probes? Was it a sign that our understanding of gravity itself broke down at such vast distances? For a time, the Pioneer anomaly became a beacon for new physics, suggesting our models of the cosmos were still incomplete. The ultimate answer, however, was not in the stars but in the spacecraft themselves. The leading theory, which eventually gained widespread acceptance, pointed to a remarkably mundane source: thermal recoil force. The Pioneer probes were powered by radioactive plutonium, which generated both electricity and waste heat. This heat radiated away from the spacecraft surfaces. Crucially, it did not radiate perfectly evenly. More heat escaped from the back of the spacecraft's dish-shaped antenna than from the front. This tiny imbalance created a net push, a photon pressure from the craft's own infrared glow, acting like a faint, continuous break. It was an exquisitely subtle effect that original mission planners had not fully accounted for. The resolution of the Pioneer anomaly stands as a masterclass in scientific detective work. It teaches us that before we invoke shadowy new forces or hidden dimensions, we must first become archaeologists of our own technology, searching for every last whisper of heat and light in the silent void. While the Pioneer mystery pointed to a hidden heat signature, other spacecraft have experienced forces that cannot be so easily explained away. This brings us to two more Earth-centric puzzles, anomalies tied to the very planet we call home. The first is known as the flyby anomaly. To reach the outer solar system, mission planners often use a clever trick called a gravity assist. A spacecraft swings close to a planet, stealing a tiny bit of its orbital momentum to slingshot itself farther and faster. The math for these maneuvers is exquisitely precise, a ballet of celestial mechanics. Yet on several occasions, something went slightly off script. When the Galileo probe swung by Earth in 1990, and again when the Near spacecraft did so in 1998, tracking stations recorded a tiny, unexpected increase in their speed. The change was minuscule, on the order of a few millimeters per second, but it was consistent and real. These craft received an unplanned boost, a mysterious little push as they whipped around our planet. No conventional effect, from atmospheric drag to radio signal pressure, could account for it. It was as if Earth itself gave them an extra, secret nudge on their way. This leads directly to the second, even stranger Earth-related puzzle. Not only do our departing spacecraft show odd behavior, but Earth's own orbit seems to hold a subtle secret. Scientists meticulously measure the planet's trajectory, and they have detected inexplicable, tiny changes in its orbital energy. The entire Earth-Sun system appears to gain or lose a minuscule amount of energy in ways that current models cannot reconcile. Think of it like this: you are driving a car on a perfectly flat, straight highway with the cruise control set. Yet your speedometer occasionally flickers, showing you are suddenly going just a fraction of a mile per hour faster or slower for no apparent reason. That is the scale of the mystery we are talking about with Earth's orbit. Both the flyby anomaly and these orbital energy whispers point toward something profound. They suggest there may be subtle, unmodeled forces at play within our own cosmic neighborhood, or perhaps they reveal a subtle limitation in our understanding of gravity itself on the grand planetary scale. These are not errors in measurement, they are the universe asking a very quiet, very persistent question. If our best models of motion and gravity cannot fully account for the path of our own home planet, what other surprises are woven into the fabric of space around us? These whispers from Earth's orbit pull our gaze outward to the frozen frontier where the sun is just a bright star. Here, beyond Neptune, lies the Kuiper belt, a vast donut of icy debris left over from the solar system's birth. For decades, astronomers have catalogued its inhabitants, expecting to find more and more objects as they mapped farther out, but then they hit a wall. Around 50 astronomical units from the Sun, the population of Kuiper belt objects doesn't just thin out, it plummets. It's as if you were walking through a dense forest that suddenly gives way to an empty, barren plain. This is the Kuiper Cliff, a sharp and unexpected boundary that our current models of solar system formation cannot easily explain. Gravity from the known giant planets should have scattered material much farther out. So what swept this region clean? The mystery deepens with the discovery of objects that shouldn't be there at all, at least not in their current orbits. Take the dwarf planet Sedna. Its path is a cosmic tightrope walk of staggering proportions. At its closest approach, Sedna swings to within 76 astronomical units of the Sun, already far beyond Pluto. But then it makes a lonely, multi-thousand-year journey outward to a breathtaking distance of over 900 astronomical units before falling back again. This is not a normal Kuiper belt orbit. Crucially, Sedna's path never brings it close enough to Neptune for the ice giant's gravity to have sculpted such a trajectory. It is an orbit detached, an icy wanderer seemingly isolated from the planetary dance that shaped everything else. Sedna is not alone. Several other extreme objects share this peculiar characteristic, their orbits clustered in space, all pointing in similar directions and tilted at similar angles. This clustering is the real clue. If these orbits were randomly oriented, it would just be strange luck, but their alignment suggests a common architect, a persistent gravitational hand guiding them over billions of years. This is where the hypothesis of Planet 9 takes center stage. The idea is that a planet, perhaps 5 to 10 times the mass of Earth, orbits the Sun on a highly elongated path hundreds of times farther out than our own world. Its immense gravity, exerted over eons, could act as a cosmic shepherd. It might have carved the Kuiper Cliff by clearing out a zone of instability. More compellingly, its slow, distant tug could explain the clustered, detached orbits of Sedna and its siblings, herding them into their strange, synchronized path. We have not seen this world yet, but its signature may be written in the skewed paths of the ice dwarfs it left behind. The search is a modern-day celestial hunt, where the prey is not a point of light, but the ghostly influence it exerts on the darkest reaches of our own cosmic backyard. The search for Planet 9 is a quest driven by the strange paths of distant ice, but the very method of its pursuit has a legendary precedent. Over a century before we dreamed of hidden worlds in the Kuiper belt, astronomers performed a similar feat of celestial deduction with the planet Neptune. Its discovery is the story of an orbital anomaly so compelling it pointed a telescope to the exact spot in the sky. In the early 1800s, Uranus was the known frontier of the solar system. Yet as observers tracked its motion, they found it stubbornly refused to follow the path predicted by Newton's laws, even after accounting for the gravity of Jupiter and Saturn. It would drift ahead of schedule, then lag behind, as if an unseen hand was gently tugging it off course. The discrepancy was small but undeniable, a cosmic hiccup that demanded an explanation. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently tackled the puzzle. They worked backward from the wobbles of Uranus, calculating that the gravitational pull of an unknown, more distant planet must be the cause. Le Verrier sent his predicted coordinates to the Berlin Observatory, and on the night of September 23, 1846, astronomer Johann Gottfried Galle pointed his telescope and found Neptune within 1 degree of the predicted position. It was a breathtaking triumph of pure mathematics over the sky, proving that anomalies were not flaws in theory, but signposts to new discoveries. This history makes the modern data from these ice giants so intriguing. Today, with vastly more precise tracking from spacecraft like Voyager 2, we can measure the orbits of Uranus and Neptune with incredible fidelity. And while most of their motion is now explained, there linger subtle, residual mismatches. Tiny wobbles persist that cannot be fully accounted for by their known interactions with each other and the rest of the solar system. These are whispers on the scale of the original Uranus anomaly that led to Neptune's discovery. Could these minute discrepancies be the gravitational signature of something else? Perhaps they are echoes from the hypothetical planet 9, its immense distance exerting a faint, steady pull on these giant worlds. Or maybe they hint at a massive, yet unseen, disk of icy debris in the far outer solar system, whose collective gravity tugs at the ice giants. The ghost of Leveria's success asks us a tantalizing question. If tracking one anomaly revealed Neptune, what undiscovered reality might these modern, microscopic wobbles be trying to show us now? The story of Neptune's discovery reveals how orbital quirks can point to hidden worlds, but sometimes an orbit itself is the revelation. Consider Pluto. For generations, it held the title of our 9th planet, a lonely speck in the outer dark. Yet its path was always an oddity, a clue that something was fundamentally different. While the 8 major planets orbit the Sun in nearly the same flat plane, like marbles rolling on a table, Pluto breaks all the rules. Its orbit is tilted at a dramatic 17-degree angle, a steep incline that takes it far above and below the orderly dance of the other worlds. Even more strikingly, its elongated path actually crosses inside Neptune's orbit for 20 years of its 248-year journey. For a brief period, Pluto is closer to the Sun than Neptune is. This should be a recipe for cosmic chaos, a gravitational showdown that would inevitably lead to a collision or a violent ejection. Yet for billions of years, this has not happened. The secret is a delicate gravitational ballet known as orbital resonance. For every 3 trips Neptune makes around the Sun, Pluto makes exactly 2. This stable, repeating rhythm ensures that whenever Pluto crosses Neptune's orbital lane, the ice giant is always on the opposite side of the Sun. They are locked in a perfect, perpetual avoidance pattern, a celestial timing that prevents disaster. This peculiar orbit, so inclined and intertwined, was the first major clue that Pluto was not like the other planets. It behaved more like the other icy objects being discovered in the Kuiper belt, many of which share similar tilted and resonant paths. Pluto's anomalous trajectory was not a planetary feature, it was a membership card to a vast population of icy bodies. When the International Astronomical Union formalized the definition of a planet in 2006, this orbital context was crucial. A key criterion was that a planet must have cleared its orbital neighborhood of other significant bodies. Pluto, sharing its orbital space with countless other Kuiper belt objects and locked in resonance with a giant planet, clearly had not. Its strange, tilted path was the physical proof that reclassified it as a dwarf planet. Pluto's orbit did not just change its own status, it reshaped our entire mental map of the solar system, expanding it from a tidy system of planets to a dynamic, layered structure with a bustling, icy frontier. Its anomaly taught us that sometimes the path an object follows tells you more about its true nature than its size or its name ever could. Pluto's tilted dance is a gentle introduction to a far more extreme gravitational game. Some objects in the distant solar system don't just have inclined orbits, they have wildly eccentric and steep paths that seem to defy logic. How can an orbit be both incredibly stretched out like a long, thin ellipse and also severely tilted high above the solar system's plane? The answer lies in a subtle cosmic mechanism known as the Kozai resonance. This is not a collision or a simple tug, but a sophisticated, long-term gravitational exchange. Imagine a small, icy body orbiting the Sun, but under the distant, watchful influence of a much more massive object, like a hypothetical planet 9 or even a passing star. Over millions of years, this distant giant's gravity acts like a cosmic broker. It facilitates a trade. The small object can exchange some of its orbital inclination, its tilt, for more eccentricity, making its path more elongated. Or it can trade eccentricity for more tilt. It's a dynamical seesaw where one characteristic goes up as the other goes down, all mediated by that distant, unseen hand. This is precisely the bizarre signature we see in several of the most extreme trans-Neptunian objects. Their orbits are not just randomly weird, they are weird in a very specific coupled way, showing both high eccentricity and high inclination. This clustering of orbital angles isn't just a curious pattern, it's a fingerprint. It's the expected outcome if these icy bodies have been slowly, methodically shepherded by the gravity of a massive perturber over the age of the solar system. So, when astronomers find a family of objects with these peculiar, linked orbits, they aren't just looking at a collection of random outliers, they are reading a history book written in gravity. The Kozai mechanism provides the pen, and the hypothesized planet 9 provides the author. Each new discovery of an object with this dual signature is another data point, another clue narrowing down the possible location and mass of the hidden architect. It transforms the hunt from a blind search into a targeted investigation, following the trails left in the twisted paths of ancient ice. The twisted orbits of distant ice hint at a hidden architect within our solar system, but sometimes the architect comes from another star entirely. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving point of light. Its trajectory was immediately shocking. This object, named Oumuamua, was not orbiting the Sun. It was on a hyperbolic path, a one-way ticket that confirmed it as our first known visitor from interstellar space. It had been drifting between stars for millions, perhaps billions, of years before its fleeting encounter with our solar system. The discovery alone was historic, but the real mystery began as it sped away. Precise tracking revealed that Oumuamua was not just coasting under the Sun's gravity. As it departed, it exhibited a tiny but clear non-gravitational acceleration, a slight extra push that modified its path in a way pure gravity could not explain. This was an orbital anomaly in real time, a deviation that spoke directly to the object's physical nature. For comets, such accelerations are common, caused by outgassing. As a comet's icy surface heats near the Sun, it vents gas and dust, creating a visible coma and tail that act like a natural rocket engine. But Oumuamua showed no coma, no tail, no detectable outgassing at all. It appeared as a silent, dark, and oddly elongated rock. So what was pushing it? The debate that followed was intense and public. One camp argued it must be a comet after all, an exotic one with very unusual dust or gas that our instruments simply failed to see. Another, more speculative possibility suggested it could be something far more exotic, a thin shard of solid hydrogen or nitrogen ice, slowly eroding in sunlight, or even, as a few scientists proposed, a light sail of artificial origin. This latter idea, while captivating, lacked definitive evidence and remained a fringe hypothesis. The core lesson, however, is profound. Oumuamua's anomalous acceleration transformed it from a mere celestial passerby into a cosmic puzzle box. Its path became a diagnostic tool. That tiny deviation from a pure gravitational trajectory was a message telling us the object was not inert. It was actively interacting with its environment, even if we could not directly see how. The anomaly forced us to confront the limits of our categories, revealing that the first visitor from another star system did not fit neatly into our definitions of comet or asteroid. It was something new, and its strange departure speed is the only clue we have to its true composition. In the silent, dark expanse between stars, even the smallest wobble in a path can shout volumes about where an object came from and what it is made of. Oumuamua's fleeting visit reminds us that our solar system is not an island, but a participant in a wider, dynamic galaxy. This raises a profound and unsettling question about our own cosmic neighborhood, one that forms the grandest anomaly of all. Is the solar system itself stable? For centuries, we envisioned the planets as timeless gears in a perfect celestial machine, their orbits unchanging over the eons. the reality, revealed by modern mathematics and immense computer simulations, is far more precarious and fascinating. This is the challenge of the n-body problem. When you have just two objects like the Earth and the Sun, their gravitational dance is perfectly predictable. But add a third, then a fourth, then 8 planets, hundreds of moons, and millions of asteroids, and the equations become impossibly complex. Each body tugs on every other, and these tugs are not constant. They change with every shift in position. The result is a system of staggering sensitivity, where the tiniest change in a planet's starting position or speed can lead to wildly different outcomes millions of years down the line. This is chaotic dynamics. It means that while we can predict the planet's paths with incredible accuracy for the next few million years, beyond that, the future becomes fundamentally foggy. The solar system is not a clock. It is a living, breathing entity with a memory of every gravitational nudge. Running supercomputer simulations of this chaotic dance forward in time yields startling possibilities. Most often, the planetary orbits continue their familiar, rhythmic waltz, but in a small percentage of these virtual futures, something dramatic occurs. The gentle gravitational resonances that keep the system in check can sometimes amplify, like a child on a swing being pushed at just the right moment. Over hundreds of millions of years, Mercury's slightly elliptical orbit could become more and more exaggerated. In the most extreme scenarios, this buildup of orbital energy could lead to a cosmic game of gravitational pinball. Mercury might be flung inward toward the Sun, or sent on a collision course with Venus, or even be ejected from the solar system entirely. The chance is minuscule on human timescales, but over 5 billion years, it is a real part of the system's potential story. This long-term instability is the ultimate orbital anomaly. It tells us that the orderly arrangement we see today is not a permanent fixture. It is a snapshot in an endless film of gravitational evolution, a fragile balance that has held so far through luck and delicate dynamical truces. Our home in space is not a finished sculpture but a work in progress, its final form still being written by the silent, relentless mathematics of gravity. Chaos governs the long-term fate of our solar system, yet within that turbulent dance, pockets of perfect calm can persist for billions of years. These are the Lagrange points, cosmic parking spots where the gravitational pulls of two large bodies, like the Sun and a planet, balance perfectly with the orbital motion of a smaller object. Of the 5 Lagrange points in any two-body system, 2 are especially magical. The L4 and L5 points lie along a planet's orbit, one 60 degrees ahead and the other 60 degrees behind, forming the tips of 2 equilateral triangles with the Sun and the planet. These are not just mathematically neat, they are dynamically stable. An object placed there, like a spacecraft or an asteroid, will gently oscillate or librate around that point, held in a gravitational embrace as it orbits the Sun in lockstep with the planet. It is a celestial harmony, a safe harbor in the gravitational sea. The anomaly lies in the distribution of the natural residents of these harbors, the Trojan asteroids. Jupiter, the solar system's gravitational titan, hosts immense swarms of thousands of Trojans at its L4 and L5 points. These are not trivial rocks, they constitute a population comparable to the entire main asteroid belt. Yet Earth, for most of history, was thought to have none. This stark difference is a profound clue. Jupiter's massive gravity acts like a cosmic fishing net, easily capturing and retaining asteroids into its stable points over the eons. For a smaller planet like Earth, holding onto a Trojan is far more difficult. The gravitational tugs from other planets, especially Venus and Mars, can easily perturb an object out of our delicate Lagrange points. So for a long time, Earth's Trojan points were considered empty, swept clean by the messy dynamics of the inner solar system. That changed with the discovery of 2010 TK7, and more recently, the confirmation of 2020 XL5, a kilometer-wide asteroid dancing stably at Earth's L4 point, leading our planet around the Sun. Finding these objects was a technical triumph, spotting a dark rock against the glare of daylight. Their existence tells us that capture is possible, but their rarity confirms the fragile nature of our local gravitational environment. The populations of Trojans are therefore a historical record. Jupiter's vast swarms suggest it formed farther out and migrated inward, sweeping up primordial material into its Lagrange points during the solar system's violent youth. Earth's lonely, fleeting Trojans, by contrast, speak to a dynamic and disruptive history closer to the Sun, where stable orbits are a precious and temporary commodity. Each Trojan, whether in a vast swarm or solitary confinement, is a fossilized piece of orbital architecture, marking where gravity and motion achieved a perfect, if temporary, truce. The delicate balance of Trojan points shows how fragile orbital stability can be, a lesson written in fire and ice around the solar system's blue giant. Neptune, a world of deep azure and supersonic winds, is guarded by a moon that defies all expectation. Triton is a frozen, geologically active world slightly larger than Pluto, but its most shocking feature is its path. Triton orbits Neptune backwards. Every other large moon in the solar system orbits its planet in the same direction the planet spins, a prograde motion that suggests a shared origin from a spinning disk of material. Triton's retrograde orbit is a glaring violation of this rule, a clear sign it is an intruder. This moon is not a native of the Neptunian system. It is a captured citizen of the Kuiper belt, a king from a distant realm brought to heel by immense gravity. The capture of an object as massive as Triton could not have been gentle. It was a cataclysmic event that reshaped an entire planetary system. Astronomers believe Triton did not arrive alone. It was likely part of a binary pair, two icy bodies orbiting each other as they drifted in from the deep freeze. As this binary system passed too close to Neptune's gravitational well, a complex dance unfolded. One member of the pair was stolen, captured into a wildly eccentric orbit, while its partner was flung away at tremendous speed, carrying off the excess orbital energy that allowed the capture to happen. This gravitational slingshot, a cosmic robbery, left Triton as Neptune's prisoner. The aftermath was brutal. Triton's initial orbit would have been a long, plunging ellipse that plowed directly through any pre-existing family of moons orbiting Neptune. The resulting gravitational chaos would have been apocalyptic, scattering, shattering, or ejecting Neptune's original satellites into the void. The moons we see today, like Nereid with its bizarre, stretched orbit, are likely the survivors of this ancient demolition derby, or perhaps new objects that coalesced from the wreckage after Triton's orbit was gradually circularized by tidal forces. Today, Triton itself is a frozen archive of that violent history. Its surface, young and remarkably smooth with few craters, tells of recent geological activity, likely driven by tidal heating from Neptune's relentless pull. Its composition, rich in nitrogen and water ice, is a direct chemical fingerprint of the primordial Kuiper belt. By studying Triton's orbit and its frozen geology, we are not just looking at a moon, we are reading the opening chapter of the outer solar system's story, a tale of gravitational piracy written in ice and orbital defiance. Triton's violent capture is a single, dramatic event in the outer darkness, but it hints at a far greater upheaval that once shook the entire solar system. For decades, the orderly orbits we see today presented a puzzle. Why is the asteroid belt so depleted? What caused the late heavy bombardment, that ancient rain of asteroids that scarred the moon? The answers lie in a revolutionary idea called the Nice model, named for the French city where it was developed. This theory proposes that our giant planets did not form where they orbit now. In the solar system's first few 100 million years, Jupiter, Saturn, Uranus, and Neptune were packed much closer together, nestled inside a vast disk of leftover planetesimals, the building blocks of planets. Their dance was initially stable, but it was destined to fall apart, as these giants interacted with the sea of icy and rocky debris around them. A slow-motion gravitational chain reaction began. The key moment came when Jupiter and Saturn fell into a precise orbital resonance. For every one orbit Jupiter made, Saturn completed exactly 2. This resonant lock sent powerful, rhythmic gravitational waves through the entire system. The effect was like pushing a child on a swing at the perfect moment, each push adding more energy. The resonance destabilized everything. Jupiter, the most massive, moved slightly inward toward the Sun. Saturn, Uranus, and Neptune were flung outward, their orbits ballooning into the positions we see today. This grand migration was not a gentle drift. It was a gravitational hurricane that reshaped the solar system's architecture in a relatively short, violent burst. As the giants moved, their immense gravity acted like cosmic plows, scattering the primordial disk of planetesimals in all directions. Some were flung inward, bombarding the inner planets in the cataclysm we call the Late Heavy Bombardment. Others were hurled outward to great distances where they coalesced into the Kuiper belt, that ring of icy bodies beyond Neptune. The fastest and farthest flung of all formed the Oort Cloud, a spherical shell of trillions of comets at the very edge of the Sun's gravitational influence, nearly a light year away. This single model of planetary migration explains a staggering array of orbital anomalies. It accounts for the oddly spaced orbits of the giants themselves. It explains the curious populations and eccentric orbits of asteroids and comets. It even provides a plausible mechanism for capturing moons like Triton, as the migrating Neptune plucked it from the chaotic Kuiper belt. The NICE model paints a picture of our solar system not as a static monument, but as a dynamic, evolving entity that endured a period of profound turmoil in its youth. The peaceful orbits we calculate today are the echoes of that ancient chaos, the settled dust after a storm that defined everything that came after. The Oort Cloud is a vast, spherical reservoir of comets, a frozen archive at the solar system's outermost edge. Most of its residents drift in slow, patient orbits, taking millions of years to complete a single journey around the Sun. Occasionally, a gravitational nudge from a passing star or a molecular cloud will dislodge one, sending it plummeting inward on a fantastically long elliptical path. We see these as the great long-period comets, visitors that grace our skies once in millennia. Yet within this pattern lies a fascinating deviation. While most inbound comets have orbital eccentricities very close to 1, meaning their paths are extremely stretched ellipses but still bound to the Sun, a rare few are measured with an eccentricity greater than 1. This number is the key. An eccentricity of exactly 1 is a parabola, an open curve. Anything above 1 is a hyperbola. In practical terms, a hyperbolic orbit is not an orbit at all in the traditional sense. It is an escape route. An object on such a path is not bound to our solar system. It is merely passing through, using the Sun's gravity to bend its trajectory before speeding back out into interstellar space forever. The immediate question is, where do these hyperbolic comets come from? There are 2 primary possibilities, and distinguishing between them is a cosmic detective story. The first and most common explanation is a gravitational assist from within our own system. A comet originating from the Oort Cloud can fall inward on a normal, bound elliptical orbit. But if it makes a close pass by a massive planet, especially Jupiter, the planet's gravity can act as a slingshot. This interaction can add enough energy to the comet's motion to boost its eccentricity above 1, effectively kicking it out of the solar system. Its hyperbolic path is not its original state, but a consequence of a planetary encounter on its way in. The true anomaly, and the object of intense scientific search, is the second possibility, a comet that is hyperbolic from the moment it enters the inner solar system. This would be a true interstellar comet, a visitor born around another star, drifting through the galactic void until our sun's gravity captured it for a brief, brilliant visit. For a long time, every hyperbolic comet discovered was later traced back to a planetary kick, making them exiled members of our own solar family. That changed dramatically with the arrival of two objects. The first was Oumuamua, which we discussed, a rocky interloper with a clear hyperbolic trajectory. The second, and even more definitive, was Comet 2I Borisov, discovered in August 2019. Borisov looked and behaved exactly like a solar system comet, with a visible coma and tail of dust and gas as it neared the Sun. But its orbit was unmistakably and profoundly hyperbolic from the outset. No gravitational interaction with Jupiter or any other planet could explain its high incoming speed. Borisov was the first confirmed, unaltered interstellar comet, a pristine piece of another star system passing through our own. Finding these objects transforms our understanding. Each true hyperbolic comet is a physical sample from a completely different planetary system. By analyzing its light, we can learn about the chemistry and conditions around its home star. Their frequency tells us about the population of such free-floating icy bodies in the galaxy. The search for hyperbolic orbits, therefore, is not just about cataloging paths. It is about opening our doors to the galaxy, one icy messenger at a time, and realizing that our solar system is not just sending material out, as with the Pioneer probes, but is constantly receiving visitors from the vast stellar ocean around us. The arrival of interstellar comets reminds us our solar system is part of a grander galactic flow, but one of the greatest orbital mysteries is written in the ancient rocks beneath our feet. Billions of years ago, our Sun was a different star. Nuclear fusion in its core was still maturing, making it about 30% dimmer than it is today. By the simple logic of sunlight, the early Earth should have been a global snowball, a frozen world locked in ice from pole to pole, yet the geological record screams the opposite. We find evidence of liquid water, of riverbeds and oceans from a time when our planet was barely 500 million years old. This is the faint young sun paradox, a profound mismatch between the energy we received and the climate we know existed. How did Earth stay warm enough for life to begin under a faint, cool sun? The answer may lie not in the star itself, but in the precise and ever-changing dance of our planet's motion. Our world's climate is exquisitely sensitive to the amount and distribution of sunlight it receives, and this is governed by a trio of subtle orbital rhythms known as Milankovitch cycles. The first is eccentricity, the slow stretching and squashing of Earth's orbit from a near circle to a slight ellipse over a 100,000-year cycle. The second is axial tilt, the wobble of our planet's angle between about 22 and 24.5 degrees on a 41,000-year timetable. The third is precession, the slow, wobbling spin of Earth's axis, like a top winding down, which changes which hemisphere is tilted toward the Sun at our closest approach over a 26,000-year cycle. Today, these cycles are the pacemakers of the ice ages, gently nudging global temperatures by altering where and when sunlight falls. But in the deep past, gravitational interactions with the other planets, especially the giants, were different. The solar system was a more compact, dynamic place. This means Earth's Milankovitch cycles could have operated with different strengths and rhythms. Imagine a scenario where, in that ancient era, Earth's orbit was slightly more elliptical, bringing it periodically closer to the faint sun for a stronger dose of warmth. Or perhaps its axial tilt was more pronounced, creating more extreme seasons that prevented permanent ice from taking hold at the poles. These orbital configurations, forced by the gravitational tugs of a younger, closer family of planets, could have provided the extra climatic nudge needed to keep the oceans liquid. It is a beautiful synthesis of celestial mechanics and planetary science. The very same gravitational dances that might one day threaten Mercury's stability could, in the distant past, have been the gentle hand that cradled our infant world in a habitable embrace. The paradox of the faint sun forces us to see Earth not as an isolated greenhouse, but as a participant in a vast gravitational system, where the tugs of Jupiter and Saturn, written into the slow codes of our orbit, may have been the unsung heroes in the story of how life first gained a foothold. The warmth of our young planet was shaped by celestial rhythms, but another gravitational dance much closer to home is actively reshaping our world and our sky. Our moon is in a slow, measured retreat. Laser reflectors left on the lunar surface by Apollo astronauts allow us to measure its distance with pinpoint accuracy, revealing that the moon is moving away from Earth at a rate of about 3.8 centimeters every single year. This is not a mystery in the sense of an unknown cause, but it is a profound orbital anomaly with immense consequences, a clockwork change driven by the physics of tides. As Earth rotates, its oceans bulge slightly toward the moon, pulled by lunar gravity. But because Earth spins faster than the moon orbits, this watery bulge is dragged a little bit ahead of the direct line between the two bodies. That offset bulge, in turn, exerts its own gravitational pull on the moon. This gentle, constant tug acts like a booster, feeding energy into the moon's orbit and pushing it into a gradually higher, slower path. The energy for this boost comes from Earth's own rotation. The gravitational friction of those tidal bulges dragging across the ocean floors acts as a brake, ever so slightly slowing down our planet's spin. It is a cosmic exchange of angular momentum, a transfer of spin from the primary to its companion. We can project this exchange far into the future. As the moon recedes, Earth's day will grow longer. A distant tomorrow will hold days not of 24 hours, but of 30, then 40. Total solar eclipses, that breathtaking cosmic coincidence where the moon perfectly covers the sun's disk, will become a memory of the past. As the moon's apparent size in our sky shrinks, it will no longer be able to completely block the sun, leaving only annular eclipses, rings of fire in the sky. And in the ultimate end state, billions of years from now, this dance will conclude. Earth's rotation will slow until one side permanently faces the moon, achieving a mutual tidal lock. Our world will have a moonlit hemisphere and a lunar-free hemisphere, with the moon hanging motionless in the sky of one half of Earth, a fixed monument in the heavens. This measured retreat transforms our understanding of orbital anomalies. They are not just static puzzles to be solved, but active engines of planetary evolution. The same gravitational forces that cause tiny, puzzling wobbles in distant orbits are, right here and now, patiently lengthening our days and stealing our moon, rewriting the very experience of time and sky on a planetary scale. Our moon's measured retreat is a direct result of a gravitational embrace so profound it has frozen an entire hemisphere in time. Look up at Jupiter through a telescope and you will witness the same phenomenon on a grand scale. Its four largest moons, the Galilean satellites, each keep one face permanently turned toward the giant planet, just as our moon does toward Earth. This is not a coincidence, but a universal outcome dictated by gravity and time, a state known as tidal locking. The process begins with asymmetry. A moon is never a perfect sphere, and even a slight bulge or irregularity creates a handle for gravity to grasp. As the moon orbits, the planet's gravitational pull exerts a stronger tug on the closer, slightly bulging side. This differential pull acts as a brake, relentlessly slowing the moon's own rotation on its axis. Over millions or billions of years, this braking force works until the moon's rotational period perfectly matches its orbital period. One revolution around its axis takes exactly the same time as one trip around the planet. The moon is then locked, forever showing its parent world the same cratered face, while its far side remains a hidden landscape, never visible from the planet below. What transforms this from a simple physics lesson into a fascinating anomaly is the incredible diversity in locking timescales across our solar system. Our own moon achieved this lock billions of years ago, a testament to its ancient and intimate dance with Earth. Jupiter's large moons are similarly locked. Yet other moons, like Saturn's Hyperion, tumble chaotically, never settling into a stable rotation. This variation is a treasure trove of information. The time it takes for a moon to become tidally locked depends on several key factors: its distance from the planet, its initial rotation speed, and most intriguingly, its internal structure. A moon with a solid, rigid interior will resist the gravitational braking for much longer than a moon with a softer, more malleable interior. Think of it like spinning two different objects on a table. A solid billiard ball will spin freely for a long time, while a ball of soft clay will quickly deform and slow. Therefore, the current spin state of a moon is a direct clue to its geologic heart. A moon that is locked tells us it is either old enough to have completed the process, or it has a dissipative interior, perhaps with a subsurface ocean or a warm, ductile layer that allowed tidal forces to work efficiently. A moon that is not locked, like Hyperion, suggests a rigid, perhaps porous interior that has resisted tidal braking, or a history of violent collisions that knocked it out of sync. By mapping which moons are locked and which are not, planetary scientists can infer the hidden landscapes of heat and liquid beneath icy crusts. The silent, fixed gaze of these moons is not just a passive state, but an active diary, recording eons of gravitational interaction and whispering secrets about the unseen oceans and molten cores that might lie within. The silent, fixed gaze of tidally locked moons reveals a solar system sculpted by persistent rhythm, a principle that carves its signature into the very heart of the asteroid belt. Between the orbits of Mars and Jupiter lies not a uniform sea of rocks, but a cosmic ring with distinct, empty lanes. These are the Kirkwood gaps, stark voids where the population of asteroids plummets to nearly zero. They are not random absences, but precise gravitational dead zones, and their locations correspond perfectly to simple mathematical ratios with Jupiter's orbit. For example, one major gap exists where an asteroid would orbit the Sun exactly 3 times for every one orbit of Jupiter, a 3-to-1 resonance. Another gap sits at the 2-to-1 resonance, and so on. This is not a coincidence. It is the direct result of Jupiter's immense gravity acting as a cosmic metronome, setting a rhythm that eventually destroys any asteroid unfortunate enough to step into its beat. Think of a child on a swing. If you give a gentle push at random, irregular times, the swing moves a little but nothing dramatic happens. But if you push at exactly the right moment in the swing's arc every single time, you synchronize with its natural rhythm. Each small push adds a little more energy, and over many cycles the swing goes higher and higher. Jupiter's gravity does the same thing to an asteroid caught in an orbital resonance. As the asteroid completes its laps around the Sun, it returns to the same relative position near Jupiter's path again and again. Each time it does, Jupiter's gravity gives it a tiny, identical gravitational nudge. These nudges are not random, they are perfectly timed like clockwork. Over thousands, then millions of years, these periodic kicks add up. They don't push the asteroid higher, they stretch and warp its orbit, making it more and more elliptical. Eventually, the orbit becomes so eccentric that it crosses the path of Mars or even swings close to Earth. At that point, a close encounter with another planet ejects the asteroid from the resonant gap entirely, either hurling it inward toward the inner solar system or casting it out into the darkness. The gap is left behind, a silent testimony to Jupiter's long-term gravitational cleaning. The Kirkwood gaps are therefore more than just empty space, they are a fossil record of solar system dynamics. They show us that gravity is not just a force of attraction, but a force of orchestration and removal. These gaps are the reason the asteroid belt is not a denser, more dangerous field of debris. Jupiter, acting over billions of years, has systematically cleared these resonant highways, making the space between the planets far more navigable than it otherwise would be. This also solves a practical mystery: the origin of many near-Earth asteroids. Those rocky visitors that occasionally cross our path are often the very objects that were once evicted from a Kirkwood gap, their orbits perturbed until they entered a new and unpredictable dance with the inner planets. So the next time you consider the asteroid belt, do not picture a chaotic, crowded ring. See it instead as a meticulously groomed garden where the largest planet has patiently weeded out specific orbits, leaving behind a pattern of emptiness that speaks to the precise, rhythmic power of gravity over deep time. The rhythmic gaps in the asteroid belt are monuments to gravity's patience, but history holds a cautionary tale about misreading its whispers. In the 19th century, the unexplained precession of Mercury's orbit presented a genuine crisis for Newtonian physics. The solution, astronomers reasoned, must follow the same brilliant logic that had just revealed Neptune. If Uranus's wobble pointed to an unseen world, then Mercury's wobble must do the same. Thus was born the hunt for Vulcan, a hypothetical planet orbiting even closer to the Sun, its gravitational tug supposedly responsible for pulling Mercury off its predicted path. The scientific community was electrified. Amateur and professional astronomers alike trained their telescopes near the Sun during eclipses and at sunrise and sunset, searching for a faint, fast-moving dot. For decades, occasional reports of sightings surfaced, each one celebrated as a potential confirmation. Yet Vulcan remained elusive, a ghost that could never be pinned down or consistently observed. The anomaly was real, but the proposed solution was a phantom. The true resolution arrived not from a new telescope, but from a new theory of the universe. Albert Einstein's general relativity, with its revolutionary vision of curved spacetime, mathematically explained Mercury's extra precession with perfect elegance. No hidden planet was required. The anomaly was a signature of the Sun's mass warping the fabric of reality itself. The case of Vulcan versus relativity is a masterclass in the scientific process. It demonstrates how a compelling, even elegant hypothesis can be completely wrong. It shows the danger of applying a successful pattern, like finding a planet from an orbital wobble, to every new puzzle without questioning the underlying framework. This history makes the modern search for Planet 9 so fascinatingly different. Like Vulcan, Planet 9 is a hypothesis invoked to explain clustered orbital anomalies, this time in the distant Kuiper belt. But the critical distinction lies in the evidence and the context. Vulcan was a single solution to a single problem that was ultimately solved by revising fundamental physics. The Planet 9 hypothesis, however, is invoked to explain multiple, independent lines of evidence, the peculiar orbits of several extreme objects, their strange clustering, and the sharp edge of the Kuiper belt. Furthermore, unlike in the 1800s, we have not yet exhausted our current understanding of gravity, general relativity, to account for these phenomena. No new physics is required, just a new, massive object within the existing rules. The story of Vulcan teaches us humility, reminding us that anomalies are not always signposts to new worlds. Sometimes they are signposts to a deeper truth about the world we already inhabit. The search for Planet 9 proceeds with that lesson in mind, a cautious, evidence-driven hunt where every new discovery of a skewed icy orbit is scrutinized, not as proof, but as another clue in a much larger and more complex gravitational mystery. The ghost of Vulcan reminds us that not every orbital puzzle points to a hidden world, but some anomalies are the worlds themselves caught in the act of transformation. Between the orbits of Jupiter and Neptune, in a realm of giants and ice, drift the Centaurs. These are not mythical creatures, but icy planetesimals bearing a dual nature, named for the half-human, half-horse beings of legend because they blur the line between asteroid and comet. Objects like Chiron and Chariklo are cosmic nomads, and their orbits are their most telling feature. They do not circle sedately within a single planet's domain. Instead, their paths are chaotic, crossing the orbits of the giant planets in long, looping ellipses that defy simple categorization. A Centaur might swing close to Saturn, then years later dive inward past Jupiter, a gravitational pinball in a cosmic machine. This is the definitive anomaly, an inherently unstable state. An object cannot peacefully share orbital space with planets as massive as Saturn or Uranus for long. Over million-year timescales, the relentless gravitational nudges from these giants will inevitably alter its fate. The Centaurs are not permanent residents, they are travelers in transition. Most are believed to be refugees from the distant Kuiper belt, dislodged by gravitational interactions and sent on a slow-motion fall toward the inner solar system. Their journey is a one-way trip into a denser gravitational field where close encounters act as gates. A Centaur that passes too near Jupiter might be flung onto an even more eccentric path, perhaps ejected from the solar system entirely. Another might be gently steered by Saturn's gravity onto a shorter, tighter orbit, eventually becoming what we recognize as a short-period comet, destined to regularly visit the warmer realms near the Sun. This transitional nature makes them profoundly unpredictable, their long-term futures impossible to forecast with any certainty. They are celestial ephemera, here for a cosmic moment before moving on to their next form. Yet within this chaos we find stunning complexity. Take Chariklo, the largest known Centaur. Through meticulous observations during a stellar occultation, when it passed in front of a distant star, astronomers made a breathtaking discovery. Chariklo possesses not one but two thin, dense rings of icy particles orbiting it. This was utterly unexpected, a feature thought to be the exclusive domain of giant planets. How can a small, unstable icy body, barely 250 kilometers across, maintain such delicate structures? The rings add a profound layer of mystery. They suggest Chariklo may have suffered a recent collision, creating a debris disk that was shepherded into rings by the gravity of a possible tiny, unseen moon. Or perhaps the rings are a fleeting artifact of its volatile nature, ices sublimating from its surface as it nears the Sun, temporarily creating a stable ring system that will one day dissipate. The Centaurs, with their cross-planet orbits and occasional jewelry, are a living library of solar system evolution. To study them is to watch the process of planetary migration and comet formation in real time, to catch celestial objects in the midst of rewriting their own destinies under the watchful eyes of the giants. The Centaur's chaotic journeys are a prelude to the final, grandest act of gravitational scattering, one that built a sphere of ice at the very edge of darkness. If you could step far beyond Pluto, beyond the Kuiper belt, and keep traveling for another 1,000 times that distance, you would eventually enter a realm of profound quiet and cold. Here lies the Oort Cloud, a vast spherical shell of trillions of frozen comets enveloping our entire solar system like a thin, distant fog. Its existence is still hypothetical, inferred from the paths of long-period comets, but its proposed structure is itself a profound anomaly. Why a sphere? Everything else in our solar system, from the planets to the asteroid belt, orbits within a relatively flat disk like a spinning vinyl record. The Oort Cloud breaks this rule completely, forming a three-dimensional shell. This spherical shape is the crucial clue to its violent and dramatic origin. It is not a remnant of the primordial disk that formed the planets, but a cosmic sculpture carved by gravitational forces in the solar system's wild youth. The story begins with the giant planets, particularly Jupiter, in those first few 100 million years. As these behemoths migrated and jostled in the early system, their immense gravity acted like a cosmic catapult. They flung countless icy planetesimals, the leftover building blocks of planets, in all directions, not just outward, but also upward and downward, sending them on trajectories tilted high above the orbital plane. These scattered ice dwarfs were given so much energy that they traveled to staggering distances, halfway to the next star, but they were not yet free. At these extreme ranges, the Sun's gravity is incredibly weak, just a faint whisper holding them in a tenuous embrace. This is where the galaxy itself took over. Over billions of years, the gentle but persistent gravitational tugs from passing stars and even the tidal pull of the Milky Way's core further stirred this distant population. These external nudges randomized the orbits over eons, erasing any memory of their original flat disk and puffing the cloud into the vast spherical halo we theorize today. Think of it like this: the giant planets are a group of powerful pitchers hurling icy baseballs in every direction. The galaxy is the wind over immense time, gently buffeting those baseballs until they settle into a giant, slowly shifting ball of debris surrounding the original pitchers. This makes the Oort Cloud a frozen archive. Each comet within it is a time capsule holding ices and dust from the solar system's very first moments. More than that, its spherical structure is a permanent record of that ancient gravitational storm, a fossilized imprint of the chaos that once reigned when the giant planets moved and the galaxy began its long work of stirring the depths of our celestial home. The Oort Cloud is a frozen monument to ancient gravitational storms, but some of the most precise orbital measurements are happening right here, just a few hundred miles above our heads. We have filled the space around Earth with a constellation of human-made satellites, and by tracking their paths with laser precision, we have discovered our own tiny, modern anomalies. Take the LEGIO's satellites, for example. These are not complex spacecraft with instruments. They are essentially solid brass or aluminum spheres covered in laser reflectors, like high-tech cannonballs placed in very stable orbits. Scientists fire lasers at them from the ground, timing the light's return to measure their distance down to the millimeter. Over years of this meticulous tracking, a pattern emerges in the data. The orbits of these passive spheres exhibit a minuscule, unexplained precession, a slow rotation of their orbital plane that does not quite match predictions based on standard gravitational models of Earth. The discrepancy is almost laughably small, fractions of a millimeter per year in their motion, but it is persistent. This is not an error, it is a signal. These satellites have become the most sensitive laboratories we have for testing the fabric of spacetime itself. One of the forces at play is a breathtaking prediction of Einstein's general relativity called frame dragging. As Earth rotates, its mass and motion twist the very spacetime around it, like a spinning ball in a thick fluid. This dragging effect should ever so slowly pull the orbits of satellites like LEGIO's along with the planet's rotation. Measuring this effect is like trying to detect the ripple from a pebble dropped in a stormy ocean. But the laser data from these satellites has confirmed it, validating a century-old prediction with stunning accuracy. Yet, even after accounting for frame dragging, tiny residuals remain. These whispers in the data are the true anomaly. Could they be a sign of something else? Perhaps they hint at subtle variations in Earth's gravitational field from hidden mass distributions deep within the planet, or from the slow movement of continental plates and melting ice sheets altering the planet's shape. Or, more provocatively, could these satellite wobbles be the faint signature of modified gravity, a suggestion that Einstein's theory, while overwhelmingly successful, might need tiny adjustments on certain scales? Each unexplained millimeter in the path of a silent, reflective sphere is a question posed to the universe. It reminds us that the most profound tests of physics are no longer confined to massive particle colliders. They are conducted in the silent orbits of our own technological companions, where gravity writes its most subtle secrets in trajectories only lasers can read. The laser-precise orbits of Earth satellites measure whispers in spacetime, but to hear the deepest rhythms of our solar system, we must listen to the galaxy itself. This final anomaly pulls our perspective back to the grandest possible scale, to the slow cosmic tide generated by the Milky Way. Our entire solar system, with its planets, belts, and distant Oort Cloud, is not floating in empty space. It is embedded within the vast disk of our galaxy, orbiting the galactic core once every 230 million years. And just as the Moon's gravity creates tides on Earth's oceans, the collective gravitational pull of the galaxy's billions of stars, gas, and dark matter exerts a gentle, persistent tidal force on everything within our domain. This is the galactic tide, a force so diffuse and slow-acting it is imperceptible over human lifetimes, but over the eons it becomes an architect of cosmic change. Its primary canvas is the Oort Cloud, that distant, spherical shell of trillions of comets. The galactic tide does not tear this cloud apart, instead it patiently combs through it. As the solar system bobs up and down through the galactic plane on its long orbit, the differential gravity from the galaxy's disk acts like a slow-motion sieve. It gradually perturbs the orbits of the outermost comets, altering their paths ever so slightly. For most, this changes nothing, but for a comet already on the delicate edge of gravitational stability, this galactic nudge can be the final push that sends it tumbling inward, beginning a multimillion-year fall toward the warmth of the Sun. This tidal force provides a steady background drizzle of comets into the inner solar system, a baseline rate of celestial visitors set not by local planets but by our position in the Milky Way. This rhythm is occasionally punctuated by a much more dramatic event, the close passage of another star. Every few 100,000 years, on average, a star drifts close enough to our solar system to penetrate the Oort Cloud. These stellar interlopes create gravitational storms, violently shaking the cloud and dislodging swarms of comets in what astronomers call a comet shower. Evidence suggests one such shower, perhaps triggered by a passing star, may have been responsible for the late heavy bombardment that scarred the Moon and planets billions of years ago. Together, the steady galactic tide and the rare stellar passage form a dual clock mechanism governing the solar system's long-term cometary traffic. They link the fate of our tiny planetary family directly to the broader dynamics of the galaxy. The orbits we calculate, the comets we observe, even the occasional threat of an impact are not purely local phenomena. They are part of a galactic conversation, a dialogue between the gravity of our Sun and the immense, slow pull of the 100 billion suns around it. Our solar system does not exist in splendid isolation. It breathes with the rhythm of the Milky Way, its deepest mysteries and its potential dangers flowing in on the silent galactic tide. The galactic tide sets a slow rhythm for cometary arrivals, but the hunt for a hidden world within our own system represents a far more focused quest. This brings us to the modern synthesis of clues, the collective evidence pointing toward a massive, unseen planet in the outermost dark. The case for Planet 9 is not built on a single wobble, but on a constellation of strange orbital signatures that together form a compelling pattern. Consider the clustered paths of the extreme trans-Neptunian objects, those icy bodies like Sedna with orbits detached from Neptune's influence. Their orbits are not just randomly tilted and stretched, they are aligned, their closest approaches to the Sun pointing in roughly the same direction, and their orbital planes tilted in concert. This is the crucial anomaly. Gravity from the known planets should have randomized these orientations over billions of years. Their persistent clustering is like finding several compass needles all stubbornly pointing northwest instead of spinning freely, a clear sign of an ongoing external influence. Add to this the peculiar emptiness of the Kuiper Cliff and the strange orbits of some centaurs, and a coherent picture begins to emerge. The leading hypothesis proposes a single architect, a planet with 5 to 10 times the mass of Earth. Its own orbit would be a grand, slow ellipse, taking it between 400 and 800 astronomical units from the Sun, a journey lasting perhaps 15,000 to 20,000 years. From this distant perch, its immense gravity would act as a cosmic shepherd over immense timescales. It could herd the extreme objects into their clustered orbits, sculpt the inner edge of the Kuiper belt, and even influence the tilt of the entire solar system's plane. This is anomaly solving on a grand scale, connecting disparate puzzles with one elegant gravitational key. Finding this world, however, is a monumental challenge. At such distances, even a giant planet would be incredibly faint, reflecting only the tiniest fraction of the sun's feeble light. Astronomers must search for a single, slow-moving pixel of light across an area of sky hundreds of times larger than the full moon. It is a needle in a haystack search on a cosmic scale, yet the tools for this hunt are arriving. The Vera-C Rubin Observatory, poised to begin its legacy survey of space and time, will be a game-changer. This facility will repeatedly scan the entire southern sky, night after night for a decade, creating the deepest, widest movie of the universe ever made. Its powerful eye will detect millions of new solar system objects, and within that torrent of data, scientists hope to find the telltale slow crawl of Planet 9. Its path, predicted by the very anomalies it is meant to explain, gives searchers a rough map of where to look. This is the cutting edge of celestial detective work, where mathematics points the telescope, and the patient, silent gathering of light may finally confirm a world predicted by the twisted paths of ancient ice. The mathematical hunt for Planet 9 is a story told by the past, but the next decade will be written by light, captured in unprecedented detail. Two monumental projects are poised to transform our view of the solar system's outer darkness, not by searching for one world, but by mapping everything. The first is the Gaia Space Observatory, a European mission of staggering ambition. From its vantage point a million miles from Earth, Gaia is not taking pretty pictures of nebulae, it is performing the most precise stellar census in history. Its goal is to measure the positions, distances, and motions of over 1 billion stars in our galaxy with micro-arcsecond precision. To understand that scale, a micro-arcsecond is the angle a human hair would subtend if you looked at it from 1,000 kilometers away. This incredible accuracy turns every star into a potential witness. As Gaia repeatedly scans the sky, it can detect the tiniest wobble in a star's position. That wobble is the gravitational fingerprint of an orbiting planet, a telltale sign of a hidden companion tugging its parent star back and forth. While Gaia's primary target is exoplanets around other stars, its gaze holds a fascinating possibility for our own backyard. Could the cumulative gravitational pull of the hypothetical Planet 9, or even a massive distant disk of debris, induce a minuscule, rhythmic wobble in our own sun's motion against the galactic background? Gaia's data is so precise it might one day reveal that subtle stellar dance, providing a new, independent line of evidence for massive, unseen structures in our own solar system. It is a measurement of almost unimaginable delicacy, listening for the solar system's deepest gravitational bass notes by watching the sun's own quiet shuffle among the stars. Meanwhile, back on Earth, a different kind of revolution is being built on a mountaintop in Chile. The Vera-C Rubin Observatory's legacy survey of space and time, or LSST, will be a relentless, automated eye on the sky. Every few nights for 10 years, its enormous camera will capture the entire visible southern hemisphere in exquisite detail, creating a cosmic time-lapse movie of the universe. For solar system science, this is a paradigm shift from targeted hunting to total surveillance. The LSST is expected to discover millions of new asteroids, comets, and Kuiper belt objects, increasing our catalog of small bodies tenfold. In this torrent of new discoveries, anomalies are not just possible, they are inevitable. The survey's power lies in its repetition, watching how these faint points of light move over time. It will find objects with orbits so strange and unexpected they defy our current classifications, objects that make Sedna look conventional. And yes, it represents our single best chance to visually spot Planet 9. The predicted world is faint and moves slowly, but the LSST-wide, deep, and repeated scans are perfectly designed to catch such a slow-moving dot of light against the fixed background of stars. By comparing images night after night, its software will flag anything that has moved, and a distant ice giant creeping along its 20,000-year orbit would stand out as a persistent, slow crawler in a field of stationary stars. The synergy is profound. Gaia measures the precise gravitational tugs from the unseen, while the LSSD scans for the unseen itself. Together, they form a complete detective agency for the outer solar system. One listens for the whisper of mass-warping motion, the other turns on the lights to see what is casting the shadow. The next great orbital anomaly, the one that rewrites our textbooks, is almost certainly already out there, a faint speck of ice or a subtle stellar wiggle waiting for its moment in the data stream. The maps of our cosmic neighborhood are about to be redrawn, not by a single brilliant deduction, but by the patient, all-seeing gaze of a new generation of machines. These 25 anomalies are not errors in a cosmic blueprint, but its most vital features. From the wobble of Mercury that proved space-time curves to the silent retreat of our moon lengthening our days, each deviation is a message. The clustered paths of distant ice whisper of a hidden shepherd, while the chaotic orbits of centaurs show us solar system evolution in real time. The empty lanes of the asteroid belt and the spherical halo of the Oort Cloud are fossils of ancient gravitational storms. Even the precise laser tracks of our satellites record the faintest drag of a rotating Earth on the fabric of reality. Together, they reveal a solar system that is not a static museum display, but a dynamic, living puzzle still writing its story. This is the grand lesson written in orbits. Every unexplained millimeter per second, every tilted path, every strange clustering is a question posed by the universe itself. It asks us to look deeper, to question our maps, and to listen more carefully to the silent gravitational music of the spheres. So keep your eyes on the sky and your curiosity alight. Follow the data from the new telescopes and space missions, for they are turning the page to the next chapter right now. The dance of the planets is an endless source of mystery, and the next great anomaly, the clue that rewrites everything, is already out there, waiting in the dark for its moment to step into the light.